So now let's talk about what kind of stress that we have in the non-axial direction, the non-normal direction. So up until now, we've looked at normal stress. So we look at that summation of those forces how they interact normal to the surface. And once again, we can see this is all balanced by the load. So the external force is P, and it's going to be balanced by this whole limit as delta A approaches 0 of delta F over delta A, or our stress times our area. And so that gives us our definition of normal stress, load over area. So what happens when our forces is not applied axially? So this is a non-axial load. So if I look at AB, well, the axial load would be working in that direction, but it's obviously not. We're pushing on it with this motion that's going across the axis. It's 90 degrees perpendicular to it. So what I need to do is we need to draw let's draw that free body diagram again. And so, and so if we make this cut right at C, what's going to happen? Well, we have this load P that's being on the outside. If I do my summation of forces in the y direction equals 0, with up being positive, well, what happens is that we are going to have an internal force of P that is balancing out that external force that's being applied. Now, as you can see here, I left in my notes already, this is where we're going to get our force. And so we've got tau, which, once again, our Greek lowercase tau. The average shear stress is going to be the load over the area. Now, sometimes you will see this as V over A, because V would be a shearing force. The book, depending on what you're doing, will jump between P and V, so it doesn't really matter. It's just to keep a note. It's just like the same thing. It is the load over the cross-sectional area. Now notice, I specifically wrote out average here. Now, unlike normal stress, we're able to make that assumption that, well, the normal stress is pretty much uniform across the section. The average shear stress, we cannot assume this to be uniform. We're going to see it later in the class, especially when we start really focusing on shear, but you can see that we will see that the maximum tau is sometimes going to be much greater than what the average shear stress is in our material. Well, but like I said, we'll look at that in much more detail in the next chapter. So why do I care about shear? Well, we see shear in a lot of common mechanical applications, especially when we're dealing with connectors, bolts, rivets, pins. All of these are going to be a huge factor in looking at how they fail is completely within shear. And actually, shear force too comes into, especially when you're using adhesives. Things like super glue, and most adhesives are very weak in shear as opposed to axial loads. So we tend to take a look at what's going on there. And so this is the first application we've got, probably the most common. This would be called a single shear application. So what is going on here? Well, we can see that I'm pulling on A, we are pulling this way, B, we are pulling this way, and so right along that plane, we are having a shear application. So if I was going to draw a free body diagram of just, we're going to draw a free body diagram of just the bolt, well, what would be happening? Well, I would have a force being applied to the upper section of the bolt, and I would have my F prime, which is going to be equivalent to F pushing on the bottom side of the bolt. And so now what we have is we've got a situation where we need to take a look at things. So what I'm going to do is I'm going to make a cut plane right here in the middle, because I want to see what's going on inside the bolt. Because once again, stress is all about those internal forces. So if I sketch up here, there's the head of my bolt. Here's my external force being applied, is that F. And now what I have is I have to do my sum of the forces in the the X direction to figure out what my internal force is. And so typically shear forces will use the arrow with only one side on the head to represent the shear force. And so if I've got some force V there, that is my shear force. Well, I can go and calculate that out by going, okay, well, the sum of my forces in the x direction with that way being positive, well, that's going to be F minus V is equal to 0. So in this case, my shear force is going to be equal to my external force, and so then I can say, well, okay, well, my average shear is going to be that shear force divided by area, or my external force divided by the area, since they're the same. Okay, so that's pretty straightforward. What happens if we kind of flip it a little bit, and we get something like this here? And this is a double shearing application. It's called a double shear because we're going to have two different shear planes. And we can look at that. Let's draw our free body diagram basically of the bolt. And so as I look at this, I'm pulling on plate B this way, plate A this way, which is pulling the bolt that way, but then it's also pulling against the C and the D. So what ends up happening is, externally, let's apply the forces. I'm going to have some force F pushing on that bolt. Actually, let's put it over on this one here. So I'm going to have that force F pushing that way, because I'm pulling the plate this way, so it's going to be pulling it into the bolt. So that's where I'm pushing on my bolt. So what happens, though, is I've got these upper and lower plates pulling back the other way. And so they're going to be pulling back with that force of C and that force of D. So now if I look at it, I've got two planes where I'm shearing, because I've got the imbalances of forces between F and FD, and then up here I've got it between F and FC. So let's draw a free body diagram of what's going on there. And so I have externally, I'm applying my load F, and so what I'm going to have is I'm going to have an internal load on either side. So I'm going to have my force of V here. I'll have my force of V there. So those are my shearing forces. I've written them both as V's because since this is all balanced out, there's no reason for them to be any different. If we did a moment equation, we'd see that we're going to end up getting the same thing because it's symmetrical. Let's calculate in what the shear stress would be in this situation. So what we have is, remember, our average shear stress is going to be our load over our area. So in this case, that's shear load over the area. Now, as I look at it, I've got it over two areas. So let's do our sum of the forces in the x direction is equal to 0, with this way being positive. So I have F minus V equals 0. So if I go and solve this, V is going to be F divided by 2. So if I go and I plug this in, that's going to be my external force divided by twice the area. So in a double shear situation, we'll be doing that external force divided by twice the area. Now this is going to be very similar to what you're going to do in one of your strengths labs. Typically it's the first one. I'm not sure where it is in the rotation right now, where you're going to apply something in a double shear, and it's just you're going to have to remember it's over twice the area. And so if it was a triple shear, it would be over 3 times the area, quadruple shear, 4 times the area. And so that's the basics of shear stress. If you have any questions, please let me know. Otherwise, I will see you in the next video.